Among lists, trees, and graphs, graphs are the most general data structure. We begin our discussion of graphs with some initial terminology and then consider a variety of possible representations. There are numerous terms associated with graphs. Let's consider the most fundamental ones. Mathematically, a graph is usually defined as an ordered pair of sets. The first set is a set of vertices, which are also less often referred to as nodes, which is consistent with the terminology used with linked lists and trees. The set of edges is the second set. Simple graphs are ones that allow only one edge between any pair of vertices. In that case, an edge can be uniquely defined by the vertex pair. Our discussion will be confined to such graphs. In more general multigraphs, multiple edges are allowed between any vertex pair. These are referred to as parallel edges. In such graphs, edges must be defined by what is usually called an edge endpoint function. Simple graphs can be further categorized into several different types. An undirected graph is one in which the edges are considered unordered pairs of vertices. In a directed graph, the edges are ordered pairs. A weighted graph is one that has a weight associated with each edge. A path is a sequence of edges in which the ending vertex of one edge is the starting vertex of the next edge. A cycle or circuit is a path in which the starting vertex of the first edge is the ending vertex of the last edge. Having introduced some of the most basic terminology, let's now consider a number of different representations, beginning with an adjacency matrix. We should note that the adjective adjacency is used because when there is an edge between two vertices, they are said to be adjacent. An adjacency matrix is a square Boolean matrix. The entry in the cell, whose row is the starting vertex and whose column is the ending vertex, is true when there is an edge between those two vertices, and false otherwise. In an undirected graph, it would be a symmetric matrix, one in which the value in every row column is the same as what is in the corresponding column row. Alternately, a triangular matrix could be used to avoid the duplication. Assuming the matrix is square, the type declaration would consist of a constant defining the number of vertices, together with a Boolean matrix instantiated so it has the same number of rows and columns. If the graph was weighted, a similar representation could be used. However, the type of the matrix elements would be double instead of Boolean. This illustration shows an example of an adjacency matrix representation on the left of a directed graph on the right. The black squares represent true and the white false. The edge from A to B is shown by the black square in row A, column B. The edge from G to J is shown by the black square in row G, column J, and so on. Let's look at a few examples of undirected graphs and see the correspondence between the adjacency matrix and the graph. In this case, we already have the adjacency matrix, and notice that it is a symmetric matrix. And when we press the Create Other button, what it's doing is it's taking every pair of entries into the adjacency matrix and creating the graph from it. If we go in the other direction and create one, what will happen is every edge in the graph now will have two corresponding entries into the adjacency matrix. And the reason for this, of course, is the fact that in this example, what we're dealing with is an undirected graph. Another possible representation is to use an array of adjacency lists. The adjacency list could be either array lists or linked lists and would contain all vertices adjacent to the vertex that corresponds to the array element. One possible advantage to this representation is that it would be an efficient use of memory provided that the graph is sparse, meaning that there are relatively few edges compared to the number of possible edges. Using a linked list for the adjacency list, the array would be an array of linked lists. In this case, we are assuming we are using the Java linked list class. With an array list, the representation would be an array of array lists. With all of the previous representations, the number of vertices is fixed. A more general approach is to use a list of adjacency lists. Such a representation will use a linked or array list of linked or array lists that represent adjacent edges. Those choices would provide 4 possible combinations. The primary benefit of this approach is that it allows the number of vertices to grow at runtime. The basic declaration would be defined as a list of lists. Additional list instantiations would be required as every vertex was added. Using a custom fully linked list of linked lists can make the graph search algorithms more efficient. So let's consider that most general representation. A fully linked representation requires 2 types of nodes, vertex nodes and edge nodes. The vertex node would contain the name of the vertex, plus a link to the first edge node and a link to the next vertex node. The edge node would contain a link to the vertex node that represents the ending vertex and a link to the next edge in the adjacency list. We conclude with an illustration of the fully linked representation on the left that represents the directed graph on the right. The reason this approach is more efficient is that the name of the vertex is not duplicated, and it isn't necessary to traverse the vertex list to find the vertex that corresponds to the ending vertex of an edge.